Dear friends, welcome to the 11th lecture in module 3 of online course on risk and reliability of offshore structures. In 11th lecture today, we are going to talk about the design FMEA for a recent innovative structural model which are meant for ultra deep offshore platforms, what we call as offshore Triceratops. This lecture is 11th lecture in module 3, where we are essentially focusing on risk assessment and reliability applications. If you recollect what we discussed in the last lecture, we said that there are many advantages of using FMEA for mechanical, electrical, electronic and structural systems, because this is one method of risk analysis which can tell me the causes of various modes of failure and then the consequences or the effects of those failure on the overall performance of the system. If we are able to identify the ranking of this failure modes, we can always say we will be able to identify the critical component or the most vulnerable component present in that system. Therefore, one can easily identify the weakest link in a given system, which can be either redesigned or which can be bypassed in the process line. So, the cause and effect diagram, which is only talking about qualitatively the failure modes, causes for the failure and the effects of those failure on the overall performance, is actually a qualitative method technique, but I want to convert this in terms of quantifying the risk. So, I generally do this using FMEA, where I am identifying what is called the risk priority number. We already said in the last lecture, risk priority number essentially has 3 variables. The first variable, which is going to be the severity, which I call as S, let us say. This is a variable whose rating corresponds to the seriousness of an effect on a potential failure. So, this talks about the seriousness of effect on the potential failure of the overall system. I want to quantify the severity. Generally, it is quantified in a 10-point scale, quantified in a 10-point scale. Let us say severity 1 may indicate it has got very minor effects, that is, the failure of a specific component will have a very minor effect on the overall failure of the system. So, on the other hand, the component's failure will not affect significantly the performance failure of a given system. 10 obviously can indicate it has got the maximum effect or maximum effect on the system. So, based on the scale of 1 to 10, one can always assign a number which indicates relatively the seriousness of the effect of failure of that component or the mode of failure on the overall performance of the given system. The second variable is what we call rate of occurrence, which actually is a rating corresponds to the first level cause and its resultant failure. first level of cause or first level cause of any specific failure will occur in the design life of the system or the product. So, the first level cause will occur in the design life of the system or the product before any additional process controls are applied to safeguard that loss. So, occurrence is always again measured in 10 point scale. So, we will say this as O. Relatively, 1 indicates that the failure is very unlikely, it means the component will not fail at all. It is designed in such a manner that the component will never ever fail. There is no possibility or probability of failure of this component is very very low. So, we call that as 1. 10 means failure of the component is certain. So, relatively indicate a number in between 1 to 10 on a 10 point scale, and assign accordingly a relative statement saying that what is actually the rate of occurrence of the failure of that component which can cause an effect seriously on the overall system failure. The third variable what we have is detection, which we say D. Detection is again a variable which corresponds to the likelihood that corresponds to the likelihood that the detection methods or the current controls will detect the potential failure. Of the component. That is, we say that failure of the component is detectable if the component fails. Obviously, it is detectable only when it fails, not prior to that. So, detectable only when it fails. Okay. So, let us say in that case again I will convert this into a 10 point scale because I want to quantify them. If I say 1, 1 will correspond to the status that there are measures which can detect failure. And 10 corresponds to the fact that failure of the component cannot be detected at all. So, any number in between you can make a relative statement saying that what is the number assigned to that particular variable and what will be the equivalent statement which corresponds to that value. So, let us quickly write down the summary. So, we said that variables severity, detectability, occurrence, or we can say DOS, that is better, let us do it in that form, detectability, rate of occurrence and severity. So, let us say 1, 10. We would like to just summarize this. If I say detectability 1, it means that the component failure can be detected for sure, can be detected for sure, cannot be detected for sure. Okay, that is what 10 means. If I say occurrence, it indicates that the failure of the component is very unlikely. So, failure will not occur, no failure, that is 1, certainly fail, that is 10. Similarly, look at the severity, 1 corresponds to, will have a minor effect on the system, will have major consequence on the system. Okay, that is what. So, risk priority number is actually a multiplication of these 3 variables. Okay. So, I want to use this data further for my design FMEA, which I am going to discuss now. Now, interestingly, these 3 variables, detectability, rate of occurrence and severity, are to be quantified based on the data of the earlier failure scenarios. So, the numbers assigned to these variables depend on the data or the similar data of previous failures. Okay, by experience or by engineering methodology, etc. Then one can compute the risk priority number, which can identify actually the important areas of concern. So, RPN can identify the important components of concern which can cause the maximum damage or a damage to be of a very high certainty to the final product or the process line. Risk priority number actually assigns the risk also in descending order, that is the highest risk priority number should be accounted for the first attention to be focused on emergency front. So, the risk priority number whose value is very high should be attended first on emergency front. Let us say, for example, what is the maximum number we can likely get in this. Let us say I have a component for which the detectability is unnoticed, for sure you cannot detect it, let us say the value is going to be 10. Similarly, rate of occurrence, one can say the component generally will not fail, but there is a possibility that the component will certainly fail after a long time of iteration or duration or repeated usage, etc. Let us say assign 10 here also. If the failure will have a major consequence on the system, then again it is going to be 10. So, the maximum product can be 1000 for a component which will certainly fail, which can be detected or which cannot be detected 100%. It means there is a fault in the design itself, okay, because you are making a component whose detectability of failure is not noticed, for sure you will not be able to know it. So, that kind of indication of a vital component in the design is not encouraged. Therefore, one can redesign the system based upon FMEA or FMECA, which can be attended first on the emergency front. Now, generally if you have an RPN numbers for, let us say, severity, for severity more than 7, okay, attention should be paid to that component. FMEA studies are actually viewed on relative scale, that is very important. FMEA studies are to be viewed on relative scale. That is, what does it mean is, in a given system, having identified the components of that system and having identified various failure modes which are possible based upon engineering, design and expertise and experience, then one can always prioritize the risk of the component failure on a relative scale. On the other hand, FMEA study of one component or let us say one system cannot be compared with FMEA study of another system, because the components, the failure modes, the causes for the failure and the effects of the failure and the control mechanisms available to either control the failure or to detect the failure can be different for two systems. So, FMEA can be only done on a relative scale. So, indicatively the component whose RPN number is maximum should be paid attention both in analysis and design. FMEA, as we saw in the last lecture, are prepared in a worksheet form where we write down the functions of the process, the possible failure modes, the effects, the severity, the occurrences and detection possibilities in single spreadsheet, which I will show you just now. Once the actions are implemented, corrective measures are taken, then FMEA is reconducted again on the same system just to see how RPN number has now been changed, improved from the earlier scenario to the new scenario. So, recommended actions should be implemented on the system. Maybe the system is redesigned, maybe the component is redesigned, system is re-examined for FMEA study once again. Then one has got to compare the new FMEA study with that of the old one and then indicate what corrective measures have improved the design or improved the process in general. So, FMEA studies are also useful for self check on the developed product. FMEA studies are very useful in scheduling the periodic maintenance, let us try to apply this concept now, method of risk analysis, for an innovative structure. What we are going to discuss now is offshore Triceratops. To understand this, one has got to understand the functionality of the platform. All of us may not be aware what do you mean by an offshore Triceratops, how does it look like. Even if you are aware, let us look into the component level analysis of this first for understanding, then we will apply this study for an offshore Triceratops very quickly. Offshore Triceratops are essentially a kind of deep and ultra deep platforms which are meant for oil and gas exploration. Are actually innovative structural systems, innovative offshore structures meant for deep and ultra deep water explorations for oil and gas. There are variety of structures applicable to this particular regime. We can quickly name some of them: tension like platforms, what we call as TLPs, spar platforms. We can also have semi submersibles, we can also have floating, production, storage and offloading structures, what we call as FPSOs. We can also have buoyant leg structures, what we call as BLS, and in that list the recent addition is Triceratops. Tri indicates it has got 3 legged structure. It is a relatively new concept introduced by White et al. In 2005. Charles White in 2005. What are the components present in this structure? The vital components present in a Triceratops consists of, let us see, starting from the top, a deck structure, it will have buoyant legs, usually 3 in number, or let us say 3 sets of buoyant leg structures, BLS. It will obviously have a ball joint or ball joints which connect the BLS to the deck. I will show you the picture and the photograph later. It also consists of a restraining system which holds BLS to the seabed. The restraining system is usually a taut mooring. So, these are some of the vital components apart from those components present in terms of use for production, processing, exploration, drilling, etc. Kindly pay attention to the figure shown on the screen now. This is a typical image of a conceived idea of a Triceratops, where a major R&D research has been carried out in Department of Ocean Engineering at IIT Madras under my supervision. We have published couple of papers, we have indicated the research findings in the textbooks written by me. We have also patented this interestingly, and we have also applied for a technology transfer which can be useful, which has been proved that this system can be useful for ultra deep water explorations. Let us quickly see what are the components we have. This is the topside deck, which is now going to house all the topside facilities, which is meant for oil exploration. This is the buoyant leg structure set of units, which is essentially positively buoyant. The buoyant leg structures resemble a spar because they have a very deep draft. The motions of course of these BLS will be similar to that of a TLP, because each BLS is connected to the seabed using a taut mooring system, which happens in the case of a TLP also. The buoyant leg systems or structures are connected to the deck using ball joints. Ball joints has a very unique feature, they transfer only translations, but they do not transfer rotation. For example, these buoyant leg structures under wave action will be moving, and there is going to create an angle of inclination with respect to this point at the ball joint, which may cause rotation at this point, may be pitch and roll motions. These pitch and roll motions will not be transferred to the hull or to the deck, they will be absorbed by the ball joints. If the ball joint or if the BLS is being surged or being swayed or being heaved, let us say translation motions are occurring, then these motions will be transferred to the hull or to the deck, so that in translatory motion the hull or the deck and the BLS units remain monolithic, whereas in rotational degrees of freedom they are isolated. Similarly, on the top derrick, if there is a wind force which can cause moment about the bottom of the derrick on the top of the deck, the deck will have a tendency either to roll or to pitch or even sometimes yaw on an horizontal plane because of the wind load. These rotary motions will not be transferred back to the BLS. So, the rotational displacements either from the BLS to the deck or from the deck to the BLS will not be transferred. However, the translatory motions from the BLS under the wave action will be transferred to the deck, or the deck motions in translated degrees of freedom because of wind will be transferred to the BLS back. So, the ball joint presence partially isolates the deck from the BLS on rotational degrees of freedom. So, it does not transfer the rotation. So, Triceratops have many advantages as listed here. It has got better motion characteristics. The wells or the drilling wells are protected because they are laterally supported. It is a very simple structural form. It has got a very simple station keeping requirements. It is very easy to install because buoyantless structures are positively buoyant, they can be afloated in the system and then the deck can be placed over the ball joints. The system is completely reusable and relocatable. It has got a very simple restraining system which is similar to that of a TLP, does not require high strength like a TLP because the axial force on these teethers are far lesser because buoyantless structures are very highly positively buoyant systems. It is a very highly stable structure and relatively low cost because the investment in terms of commissioning, erectioning and installation is far lesser compared to that of any other parallel structure which is meant for ultra deep waters. Now, the BLS which is positively buoyant need to be supported and housed and constrained in its motion to the seabed. So, we connect them with the restraining system. Generally, the restraining system is consisting of taut mooring lines which is similar to that of a TLP. However, the initial tension which is imposed on the mooring lines or on the teethers will be far less compared to that of a TLP. Okay. So, this is a conceptual idea. Of course, as of now no offshore Triceratops are commissioned in practice, but however intense research is going on in this. You can refer to the papers listed in the NPTEL website of this particular course. You will find lot of interesting researchers working on this front, and this idea was conceived and floated and people have started working on this. We did lot of experimental, analytical, numerical investigations on this structural form and we have also published them in open domain for the benefit of researchers. So, now we are going to look at the FMEA study of this particular structure. Why I am explaining the structure? Because the functionality of the platform, the components need to be understood before we start doing an FMEA, which is a risk assessment for this particular system. Experimental investigations are carried out in IIT Madras. Please pay attention to the figure shown on the screen now. This is actually a model which is kept in the flume. The model is what I am showing here. That is the deck. This is nothing but the BLS. These are the ball joints. The BLS are commissioned to the seabed using teethers which are taut moored. The teethers are having top tension riser systems. So, there is a pulley at the bottom. The teethers are passed through the pulley and it is pulled up. So, the tension is imposed here for convenience because this is a permanent system where the load can be applied and the system is set to afloat for a design draft. So, we have done this experiment at a deep water pit which is about 4.5 meter deep and the width of the pit is about 4 meter square, and we have used a wave maker which can generate regular as well as random waves on the system. However, the system experiment is initially conducted only for regular waves, and that is the detail of the cross section where the wave is being generated and where the wave is being absorbed at the beach front. That is the plan. This is about practically 100 meter long, 50 plus 30 80 about 85 90 meter long. That is the length of the flume. The width of the flume is 4 meter. This is the deep water pit where the deeper section where the platform is installed. In plan, all the 3 teethers are aligned in such a manner that 2 legs are kept on the wave front and 1 leg is kept away from the wave front for a specific orientation. then the orientation is also changed and experiments are conducted for different layout of the tethers or the buoyant legs for a given wave directionality. Now, let us look into the components of a triceratops and the failure modes. Please pay attention to the figure shown on the screen now. Let us say offshore triceratops has got essentially two systems, substructure and the deck structure. Substructure contains the buoyant leg systems, the tethers and the ball joint. The superstructure contains the drilling string, the risers, the derrick and an LNG tank. Obviously, these are different failure modes, these are the components available in triceratops. There is a broad division of the structural components, and let us now look into the failure modes at which the triceratops can fail structurally. It can fail by fatigue because there is always correction available or applicable to the tether tension. So, fatigue failure, it can fail by bending, the ball joints can fail by fatigue, tethers can also fail by fatigue, the buoyant leg structures can fail by bending. Of course, buoyant leg structures do not fail by fatigue because there is no reversal of forces acting on them, it is a positive buoyant system. They can fail by corrosion, they can fail by extensive torsion, etc. So, all these failure modes of fatigue, bending, torsion, corrosion, snapping, collapse and buckling are connected to various possible elements or components available in a given system of assembly, what we call as offshore triceratops. Then what could be the causes for these failures? Because we have to look into the cause effect diagram. These are the failure modes. The effect of this failure could be very interesting, which we will see. Is going to only talk about the failure modes. The causes could be insufficient strength or excessive load. That is what we do in reliability. There are two factors here. One is the strength factor, other is the load factor or the resistance factor and the load effects. That is what we compare, and that is how we generally form a function which is a performance failure function of a given system, where we have been talking about in first and second modules of failure of system using reliability theories. So, there are two systems here, one can come from the strength insufficiency, other can come from excessive loads. It can be due to degradation of material, it can be due to error in design, fabrication, installation and operation, whereas excessive load can come from the environment, it can be wave load, it can be current, it can be seismic loads, it can be wind load, it can also come from excessive operations, for example sudden drop objects, etc. can also come from accidental loads, where the impacts of vessels can cause accident loads on the BLS. Interestingly friends, when the impact loads are imposed on the BLS, since BLS is isolated partially from the deck, so these impact loads will only could cause damage to the buoyant leg structure, which is not transferred to the hull. Therefore, the hull or the deck remains still safe. So, this can be seen as one of the interesting advantage of accident failure modes of a triceratops, which is essentially recommended for ultra deep waters. Please pay attention to the table shown on the screen now, which is now summarizing the components, various failure modes, various failure effects, causes and recommended actions, which is nothing but the cause, effect, summary, which is qualitative risk analysis, which is the first stage in FMEA as we discussed in the last lecture. So, if you look at for example ball joint, it can fail either by fatigue, corrosion, bending or buckling, because ball joint is subjected to PM combination, which we discussed in the last module excellently, how there can be modeling constraints in physical models when you do reliability analysis. We also worked out the moment rotation characteristics of this ball joint for triceratops. If you please look back the application problem, what we did in the last module, you will recollect that ball joints can also fail by bending and buckling modes. The failure effect can result in cracking, can cause misalignment, it can cause a total collapse of the entire structure, which can result in fatality, because ball joint is a unique connectivity between the substructure to the superstructure. So, that becomes a very vital component of the whole design, as you can see from the list here, and the causes for this failure can be a faulty design, can be manufacturing defect, can be biological and environmental factors, which can result in this kind of failure, the recommended action should be rigorous testing should be done before the ball joints are implemented in design. You should also ensure proper lubrication, so that the ball joints are free to rotate about its own axis, and one should always carefully select the material which has got a very high tensile and compressive strength as well as good resistance for number of cycles of fatigue loads. So, like that various components are assigned: BLS, teethers, drilling string, risers, derricks and LNG tanks. Various failure modes of these components, the failure effects on the overall system, causes for this failure and recommended actions are listed in the cause effect table as you see on the screen just now. Interestingly, this information is taken forward to do an FMEA study. Now, the FMEA table is very interesting, which is shown to you, which is essentially an FMECA which is done for the design purposes. That is called design FMEA. So, one can see for example here the ball joint. The function of the ball joint is to support the system, the deck weight, and it connects the deck to the BLS, that is the function. The failure modes are borrowed from the previous slide: fatigue, corrosion, bending, buckling. The effects could be cracking, misalignment, collapse of the entire structure. So, the severity is measured on a 10-point scale to a value of 4. Please pay attention to this figure here, to the table here. Severity 1 means it can cause a minor effect on the overall system. Severity 10 means it can cause a major consequence to the system. We have taken a number 4 here. One can always take a number definitely closer to 10, maybe higher than 4 or even 4 or 5, that is the severity. What is the likelihood or occurrence of this event? The likelihood or the occurrence, if you say 1, for sure there is no failure of the joint. If you say 10, for sure the joint will fail. Obviously, one will not assign a number 10 here, because one does not design a system for certainly to fail. Therefore, we have taken a number 4 here on a relative scale of 1 to 10. If you look at the failure causes, it can cause faulty design, manufacturing defect, etc. The rate of occurrence now after the corrections are made by implementing controls can be reduced to 3. So, there is a difference in occurrence from 4 to 3 if you are able to do routine checks and adoption of proper standards. However, look at the detectability. Look at the screen here. The blackboard summary says if you have a number 1, you can detect it for sure. If you have number 10, you cannot detect it. For example, micro cracks developed because of repetitive loading, because of axial load increase, because of corrosion, because of material degradation, because of loss of lubrication, generally goes undetected. Okay? But there is no guarantee that you will never be able to detect at all. Therefore, we are not assigned number 10 here, we have assigned a number 7 here. Therefore, if you look at the product of RPN, which is nothing but the variables of severity, detectability and rate of occurrence, I get this number 112. The recommended action should be, I should go for rigorous testing, proper lubrication and proper material selection. Similarly, we have done every component analysis, we have done RPN for every number, we have prioritized them, and one can see from this table very clearly that ball joints are considered to be the most sensitive, most vulnerable component whose effect can cause a very serious consequence on the overall function of offshore triceratops. Friends, let us also look into a small video which actually tells you how the isolation between the deck and the BLS happens because of the ball joint. Please pay attention to the screen now. This is nothing but a triangular deck plate which is connected to the buoyantless structures. You can see the draft design for the buoyantless structures which are calibrated here. You can also see the instrumentation being used for measuring various degrees of freedom in response. So, we are now, these are the ball joints have been shown, we are also measuring the acceleration in the ball joint, inclinations the ball joint as well. So, let us see how the, for a given system of forces, let us say lateral loads, though the ball joints, though the BLS you can see they are moving and they are rotating, but the rotation is not transferred to the deck. However, when there is a surge motion to the BLS, the whole platform is in the surge motion. So, displacements are transferred, but rotations are not transferred from the BLS to the deck at all. So, the ball joints observe these kind of rotational displacements, but they transfer the translational displacements from the BLS to the deck. So, this is very important aspect of the design. Therefore, based on this understanding only, one can now do very interestingly in FMEA, which I will show you now. So, friends, in this lecture we have understood how an FMEA study, which is one of the risk methods or assessment, can be applied to an offshore structural system. As a salient example, we have understood this is one of the innovative offshore platform which has recently diagnosed by various researchers for its suitability in ultra deep water oil exploration. So, I hope this set of lectures on risk assessment using FMEA will be helpful for you to really apply some future concepts in your office as well as in your traditional methods of design, so that you can always assess the risk involved in the design by looking into the failure of the components, its effects, causes for the failure, and improving the failure prevention, and therefore improving the overall performance of the entire system. Thank you very much.